All right, these are the notes for section 2.4, the last section of chapter 2, and the title is Rates of Change and Tangent Lines. All right, so if we look at the slope of a line, let's say that we wanted to find out what the slope was of this curve at this point right here, and we've signified it by the little black short line here. That's called a tangent line. It's going to be a line that's going to intersect our curve at one point and one point only. Now, notice it's a line segment, it's not a line. If this curve had come back across, we're talking about in the location right here near it, that it's intersecting only once. It can actually go through different points, but when we're talking about the tangent line at a point, we're talking about the point that's going to just brush up against that line or that curve right there. Now, the slope of any line is given by delta y over delta x, rise over run, y2 minus y1 over x2 minus x1. We know all this from Algebra 1. So if we wanted to approximate what this line around here is, and we've kind of hinted at this the entire time, but we're actually going to see the graphical way we're doing it as we talk now. What we can do is we can start off with taking the secant line, which is a line segment from one point on the curve to another point on the curve, and find the slope of it. So for instance, we could go from our point here at 1, 1 to the point 4, 16, which is up here. Now, if we did that, well, we would calculate our slope. Delta y over delta x equals 16 minus 1 over 4 minus 1, which gives me 15 over 3, which gives me 5. So the slope of the red line here is 5. And we can see that this slope is definitely less than that. So we know we've got at least an upper value. We know it's going to be less than 5. But can we go about finding this and be a little more accurate with it? Well, here's the thing. If we take that point that we had over at 416 and we move it back to point at 39 and calculate our slope, well, what do we notice versus that one that was way up here to here? Well, it's a little closer to what that slope of that black line is. So we can calculate it, and we're going to end up with 4. So it's a smaller value, so that means it's actually getting closer to this value. Well, the same thing is going to be true as we let this point right here get closer and closer and closer to this. So we could go to 2, 4 and calculate it, and we get a slope of 3. So notice here, we're getting even closer to equal to that slope of that black line segment there, the tangent line. But we're using secants, and we're getting closer and closer and closer. So as we got our point, our second point there with our secant line, closer and closer down here to this point right here, what do we notice about our slopes? They were approaching, getting closer to what this actual value is. So if we got really close to 1, 1, this point, perhaps maybe 1.1 and 1.21, the approximation is going to get even better. So we end up getting a slope, and this is just like this little point, this little secant line right there. We can't draw it that close without zooming up, but that's going to be 2.1 for a slope. So we're getting closer and closer, hopefully you can kind of see this, to a value that's going to tell me what this slope is. Well, how can we find this slope exactly? How close could we actually get with this? How close can we get these 2 points together? Well, we've already talked about this some in our work where we talk about using the h and the difference quotient. Well, that's all that we're going to do. So we're going to see this yet in another way here, and this is where our h comes from graphically. We have our y value that our x value that we're trying to find our slope at, which is 1, and we're going to add some value h. So our x value over here is 1 plus h. Well, then we need to find our y values. So we would find f of 1, in other words, our function value when x was 1, and our function value when x is 1 plus h, and we could put that together to get what our slope's going to be. So our slope would be f of 1 plus h minus f of 1 all over h. Now on the bottom here, we technically would have 1 plus h minus 1, but those cancel out. This would be our y2, our x2, this would be our x1. But the 1's are going to cancel out. That's why we end up with just an h on the bottom. So if we wanted to find the slope at 1.1, what we're going to do is we're going to take the limit and we're going to allow that value of h to go to 0, so that those 2 points that we're talking about are going to get really, 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 really close together. So close together they might as well be the same point. So when we do this, let's go ahead and work this out. And we're going to have to expand this. So we've got the limit as h approaches 0 of 1 plus h squared is going to be 1 plus 2h plus h squared minus 1. The 1 plus h quantity squared is where I get this. And of course the 1 is technically squared. That's where I get this. And the reason we're doing the squared is because remember we're talking about the function y equals x squared. That's what our function was to begin with. So now we can simplify. Well, we got the h there on the bottom. And we can simplify, and these 1's are going to cancel out. So we're going to be left with a limit as h approaches 0 of 2h plus h squared. Well, I can take out a common h from that, and I'm going to have h times 2 plus h all over h. And of course, these h's are going to cancel each other out. And we're left with a limit as h approaches 0 of 2 plus h. And when we take our limit, remember we're just going to let h go to 0. As h gets closer and closer and closer to 0, what's this thing going to have a value of? Well, it's going to be a value of 2. So our limit here is 2. And what are we finding here? We're actually finding the slope at this point right here. So we're finding the slope of the tangent line right there when x is 1, and it turns out that that slope is going to be 2. So we've looked at this before, but now we're going to define it in a little different way. And it says the slope of the curve y equals f of x at the point a f of a is this thing right here, which once again is nothing more than the difference quotient with a limit as h approaches 0. So the slope is the limit as h approaches 0 of f of a plus h minus f of a all over h. Same thing we've been looking at for our instantaneous rate of change. Well, the reason why is because slope is a rate of change. Slope just tells us how much the y value is going to change for any change in the x value. That's all it is. All right, and we've already talked about the fact that this is called the difference quotient, and in this case it's specifically called the difference quotient of f, since that's the function we're dealing with, at a, since that's the value we're plugging in. That could easily have just been x. In that case, it's just the general difference quotient of f. All right, so if you're asked to find the slope using the definition of slope, of instantaneous rate of change, or using the difference quotient, this thing up here is what you're going to use. You're going to use that limit as h approaches 0 of the difference quotient. All right, now the slope of a curve at a point is the same thing as the slope of the tangent line at that point. Remember we were looking at that little black line segment? Well, that was not a tangent line, and we found the slope of that line. So if we need to find the slope of a tangent line or the slope of the curve at a certain point, they're both the same thing, and we use that definition we just looked at to find those. Now, in the previous example, we could have gone one step further and found the tangent line at that point by simply plugging everything into our point slope form. Well, here's what we would have done. Remember, we found that the slope was 2, and the point we were analyzing that out was 1, 1. So if we plug all that stuff in, our tangent line for that little black line segment would have been y minus 1 equals 2 times x minus 1. Now, if you're writing a tangent line and there is a choice, you leave it just like this. Don't go any further. Do not expand it. Do not put it into point slope form or slope intercept form or anything like that. Leave it just like that. If you have to, like on a multiple choice problem, and all your choices are in slope intercept, then go ahead and do it. But if you're given the option, just plug the stuff into point slope and leave it as it is. That'll keep you from making little simple algebra mistakes that we all make. Now, if you want the normal line is just perpendicular to the tangent going through the exact same point. So, whereas we were looking just a second ago of our curve here, and we looked at our tangent line going like this, well, sort of like that. Imagine that that's tangent to that. Well, our normal line would be perpendicular to this line through the exact same point. Now, there are reasons to find the normal line, so you're going to need to know how to do that. But remember, all the difference between those two lines are, since they share the exact same point, the only difference is the slope. What's the slope? How does the slope change when you want to do a perpendicular line? Well, it's just a negative reciprocal. You flip the fraction over, or make it into a fraction and flip it over, and change the sign. So for instance, on that last case where the slope of the line, of the tangent line was 2, the slope for the normal line would be negative 1/2. We would think of that fraction as 2 over 1, flip the fraction over to get 1/2 and change the sign to a negative, and that's going to be the slope of the perpendicular or normal line to that point. Alright, so let's do a couple of things here. Let's find what the slope at x equals a would be. So all we're going to do is the same thing we just did with our limit. So we've got the limit as h approaches 0 of f of a plus h minus f of a all over h. Now, when we plug this in, we're going to put a plus h in place of x, and we're going to put a in place of x for those two expressions. So we end up with 1 over a plus h minus 1 over a all over h. And we've got our limit, forgot to put that in there, limit as h approaches 0. Alright, so we're going to have to get a common denominator here. So we're going to multiply this first one by a over a, and the second part by a plus h over a plus h. So when we do that, we're going to have the limit as h approaches 0 of a over a times a plus h. Don't distribute the denominator, just leave it like it is. You'll understand why in a second. And then minus 1 times a plus h gives me a plus h over my common denominator of a times a plus h. Now we're still over this h on the bottom. Don't lose that bottom h. We're going to need to use that in just a second. So when we combine these two, we're going to have a minus a, which gives us 0. And we have 0 minus h. Don't forget that you're subtracting everything in the second fraction. So that's a negative h. So we end up with a limit as h approaches 0 of negative h over a times a plus h all over h. Now at this point, we can do a little trick with keep, change, flip. If we're dividing by h, remember that's the same thing as multiplying by the reciprocal of h. So in place of this right here, we could just take this upper fraction up here and multiply by 1 over h. And when we do that, what do we notice? Well, these h's are going to cancel out. So we end up down here with the limit as h approaches 0 of these h's canceling out, you get negative 1 over a times a plus h. Now, Now we can take our limit. We've got this simplified as much as possible. What's going to happen is h goes to 0. Well, this term right here, the a plus h, is going to get closer and closer and closer to a. So we end up with a times a, which would be 1 over a squared, or negative 1 over a squared, sorry. So negative 1 over a squared. And that is our slope at any value of a. So if we wanted to find the slope at, let's say, 2, well, we could just plug in a 2 right here, and we're going to see that the slope is going to be negative 1/4. If we wanted to know what the slope was when a equals 7, we just put a 7 in right there, and it's going to be negative 1 over 49. So we found, essentially, when we set x equal to a, we can plug any value that we want where this function exists. We can plug in for a, and we can find the slope there. So we found all the slopes for all the points for all of this function. Now, if it says find the limit on the test, you have to show your work. In other words, you're going to have to simplify down and all that stuff. You can't just say, oh, well, the limit is such and such. Even if you can see it or you know what it is ahead of time, you've got to show the work on how you get there. All right, so if we know, like we just found, that the slope equals negative 1 over a squared, where is the slope going to be negative 1/4? So what we're asking is, where is negative 1 over a squared equal to negative 1/4? Well, the negatives would cancel each other out, and our 1s would cancel each other out. So what we can do some cross multiplication and stuff, but what we're really boiling this down to is what? What value of a is going to make a squared equal to 4? So a squared equals to 4. Take the square root of both sides, and that's going to give us a equals, remember we're solving for all possible solutions here, so that would be plus or minus 2. So what this is saying is that what we've just found out is that if we're looking for where this slope or this function has a slope of negative 1/4, it occurs at when x equals negative 2 and x equals positive 2. So if you look at those 2 points on this graph, we're going to have a slope of negative 1/4 there. All right, so a little bit of review. The average slope is nothing more than the slope of the secant line. In other words, the slope of any line that we've talked about. Delta y over delta x, rise over run, etc., etc., etc. The slope at a point is that limit thing that we were just doing. Often these two things get mixed up. Don't mix up an instantaneous rate of change, the bottom one, and an average rate of change, which is the top one. That's the difference between the two. So the slope at a point is the instantaneous rate of change, and the slope, the average slope, is the slope over a bunch of points, which means we're going to take the average from one point to another. Okay, and the same thing when we start talking about applied problems is for average velocity, which we started this whole limit thing off with, if you remember. The average velocity was just the total distance divided by the total time. Whereas the instantaneous velocity, if we have a function f of t that we know is the position function, that will tell us the position at any time, well, it's going to be this thing, which, if you know this, is the same thing as that thing. So instantaneous rate of change of velocity is a rate of change. It's the rate of change of the position. So if we're looking for any type of instantaneous rate of change, that's the equation we're going to use. And just remember, graphically, the velocity is nothing more than the slope of the position function. And we'll talk more about that when we get actually into derivatives and get into applications of derivatives in the coming chapters. All right, so here's some quick rules for you to write, to how to draw tangent lines or how to find the equations of tangent lines. I'm not going to read all this off. You guys can read it and you can copy it down and look at it. If you've got questions, you can ask those in class. But you may want to pause because I'm going to kind of hurry up here just a little bit. But there's all that. You can pause it and copy it if you want to, if you need to. But let's actually look at a problem. Okay, find the slope of the curve and the equation of the tangent line and the normal line for y equals x squared plus 4x at x equals 1. You guys try that. Since you know how to do it, we've looked at some examples. Figure out if you can put that, find the slope, put it in point slope form to get the equation of the tangent line, then do the negative reciprocal of the slope to get your...
May I have your attention, please? If you ride bus 1376, you'll ride bus
to get your normal line
1043 home
equation.
today.
That's all.
If you ride 1040,